Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our summary of our work on infinite series by taking a little look at the speeds at which different expressions grow. And this is going to be important because if those expressions are in the numerator, they're causing our terms to get larger and larger. But if those terms are in the denominator, they're causing our terms to get smaller and smaller. And we know that the chance that a series has to converge, meaning that when we try to sum up all those terms, we need those terms to get small very quickly in order to have any hope of adding them up and achieving a finite value. So, in a lot of ways, we've already hinted at the discussion that we're going to be having here. We've talked a little bit about how when working with like polynomial terms, the largest power is the power that's the most important. And we often use things like the limit comparison test to chop off the sort of unimportant terms and just examine the highest power in the numerator, highest power in the denominator. I'd like to expand on that just a little bit by sort of ordering the expressions, at least some of the sort of more basic expressions that we've encountered in terms of their speed. And then we're going to look at a series of examples where we see exactly what we mean by sort of ordering the rates of growth of these different expressions. So this list is in no way comprehensive. There's plenty of things that are not included on this, but it gives you sort of a general idea of some of the major types of expressions we encounter and their speeds of growth. So one of the slowest growing things that we encounter are logarithmic expressions, meaning something like ln of n. ln of n certainly gets larger and larger as you put in larger and larger values, but it is very, very slow. If you take like ln of 1,000 or ln of 1,000,000, you get a large number, but it's not that large compared to the input you put in. The next tier, which is a faster growing type of expression than logarithmic, are polynomial or power expressions. We mean things like n or n squared or even the square root of n. And that's why we say power expressions. In other words, n raised to some power. These polynomial expressions are faster than logarithmic ones. Even things like the square root of n grow more quickly than a logarithmic expression. If you want, again, you can sort of check that. Take a really large number like 1,000 or 1,000,000 or something. Try the natural log of 1,000. Compare that to the square root of 1,000. Square root of 1,000 is slow growing, but it's much faster than the logarithmics. Then, faster than polynomial and power expressions are exponential expressions, things like 2 to the n or e to the n, things like that, where the base is unchanging, but the exponent grows. Once again, what we mean by that is if you pick a really large number, like 100 or 1,000, you take something like 100 or 1,000 and you square it or you cube it, it gets really big. But if you take like 2 to the 100 or 2 to the 1,000, that's much, much larger because exponentials grow even faster than polynomial or power-based expressions. Now, beforehand, this is sort of where we, at the beginning of our analysis, we mostly just encountered things like this. More recently, though, we've encountered the factorial, that n factorial type expression. We saw an example when we were first introducing ratio tests where that n factorial was much, much faster than exponential terms. So again, if you test something like n factorial, like 100 factorial, and you compare it to like 2 to the 100, both are absolutely massive numbers, but the factorial is a whole level larger than the exponential. And then finally, something that we haven't really encountered too much, but we will discuss here, just to show you that this sort of, you can always find faster and faster expressions. The factorial is incredibly fast, but this n to the n, which is sort of a combination of the polynomial and power and the exponential expressions, where both the base and the exponent are growing larger and larger. So this is things like 100 to the 100th power or 1,000 to the 1,000th power. This is even faster than the factorial expression. And to sort of help you guys understand this little chart of these different expressions, we're going to do a series of examples where we start with some things that are logarithmic, then go to polynomial, then go to exponential, then go to factorial, and then go to n to the n, and see that the one that is faster is always what dictates whether or not we're encountering something that converges or diverges. But I do want to make one quick note here that's sort of spelled out in this paragraph. The examples we're about to do are hopefully going to help you guys sort of understand this series of expressions and how they are each sort of a level faster than the previous ones. But I do want to just make a general note. All of this is sort of to give you guys a better look at the behind the scenes of what's really going on when we're talking about convergence and divergence. We've already hinted at how the convergence and divergence of a series is based on how quickly the terms descend to zero. But in general, like when we're still solving questions, like when you're working on something on a quiz or an exam, you still want to always analyze it using an appropriate test. We're not introducing this as a way of saying, oh, we don't need to use the tests that we've learned. Hopefully, the real idea of this is that after this discussion, when you look at a series, you'll have a sort of sense based on this sort of ordering of expressions, whether or not something is likely to converge or likely to diverge. Then, as you're actually applying the appropriate series test, something like integral test, limit comparison, direct comparison, ratio, root, whatever you choose, you'll sort of know the most likely answer, so you'll have something that will sort of motivate your approach and help you check your results. So again, really this is more to just give you a sense of something we've been hinting at. It's not going to be sort of saying that we just rely on this to answer the whether or not a series converges or diverges. We still want to use those tests that we've learned, but this is really just to sort of expand that sort of background that we've been discussing. So let's get into some examples here. So our first one here, we're going to try to determine if this series is absolutely convergent, conditionally convergent, or divergent. So if we look at this, and now as we do these examples, we'll also get a chance to practice some of our techniques and everything. If we look at this here, certainly this has something where the terms descend to zero, right? As n goes to infinity, ln of n also goes to infinity, and since we have 1 over something that's going to infinity, we know that that's going to 0. So the terms are going to 0. In other words, the test for divergence gives us no information. So just as a note of that, test for divergence, right? No info here. But what we were sort of saying is we know that there are some power functions, right, n to different powers, that don't converge, right? We know that there's some p series that don't converge. Things like 1 over n or 1 over the square root of n or all those things, those have powers that are less than or equal to 1, and we know that those diverge. Now, like what we just said, we sort of said that the logarithmic expression is the absolute slowest of sort of the basic expressions that we encounter. So while this is growing, we don't expect it to go very quickly. So if this had been like 1 over n, this thing would still diverge because it would be the harmonic series. And this 1 over ln of n is going to 0 even more slowly. So we sort of anticipate that this thing will diverge. How can we check that? Well, you can do it several different ways, but actually probably the easiest is a direct comparison with that sum 1 over n, which we know diverges as a p series. Okay. So how would we do that direct comparison? Well, since this diverges as a p series, what we would need to show is we would need to show that 1 over ln of n is greater than or equal to 1 over n. And the proof of that is pretty easy. The proof is that n is bigger than ln of n, right? N is greater than or equal to ln of n. And you can imagine that for well, it's technically true for n greater than or equal to 1, but that's definitely true, right? If you take the natural log of something, it's going to make it a bit smaller. And then, of course, if we do the reciprocal, well, if I divide this over here and divide this over here, then certainly I would get that 1 over ln of n is greater than or equal to 1 over n. Check. So the terms of our series are always larger than the terms of the harmonic, which we know that that series, the harmonic series, diverges, so this series diverges. So we can say, by direct comparison test, sum 1 over ln of n also diverges. And this sort of shows you my first part of my statement, that the natural log is the slowest growing function. If we have a natural log in the denominator, that's not going to collapse to 0 quickly enough for the series to actually converge. And we did that by simply analyzing it compared to that 1 over n, and we saw that the terms of 1 over ln of n are bigger than the terms of 1 over n, so that series had to diverge. Okay, let's take a look at another one. Now, let's put that ln of n in the numerator. So that ln of n is causing our numerator to grow. Eventually, this numerator is going to go towards infinity. But in the denominator, let me put an n squared. Now, according to what we put back here, this polynomial or power function is faster. But not only is it faster, it's a whole level faster. And what that sort of means is that while this ln of n is going to go to positive infinity, this thing is still going to act sort of like that 1 over n squared. And now we know that 1 over n squared is something that converges. Now, it turns out that you're not able to do this through a limit comparison test, but we can actually analyze this through an integral test. So let's see if we can try to analyze this via integral test. So we're going to try integral test. So our function f of x is going to be ln of x over x squared on the interval 3 to infinity. Now, certainly that is positive. It's certainly continuous. And to check that it's decreasing, I guess we would need to do the derivative. We'd get 1 over x times x squared minus ln x times 2x over x to the 4th. And if we simplify that, that's going to be x, and it looks like we would get 1 minus 2 ln x times x there over x to the 4th. Now, I could simplify it further, I suppose, by like canceling out, but I don't really care about that. What I care about is that this is positive, and since x is from 3 to infinity, this is guaranteed to be negative. So overall, this thing is less than 0. So we now know that our function is positive, continuous, and strictly decreasing, so we know it's appropriate to apply the integral test. So we're going to examine the integral from 3 to infinity, ln x over x squared dx. Since this is an improper integral, the first thing that we want to do is rewrite it as a limit of a definite integral. And I'm going to go ahead and just set this up like that, because that x to the minus 2, we can obviously write it out of the denominator. Now, this is a nice one to use integration by parts on. So let's have our u be that ln x, so that we don't have to deal with integrating that. And our dv will be x to the minus 2 dx. du then is 1 over x dx. And v, well, if I integrate this, its new power is going to be negative 1. Divide by that, I get negative x to the negative 1. So it looks like I get the limit as t goes to infinity. We'll put some brackets. We have our uv, so it looks like we have negative x ln negative x to the minus 1, ln x minus the integral of negative x to the negative 1 over x dx, and then that's all evaluated from 3 to t. We've done ones like this many times already, so we can go pretty quick here. This is negative x to the negative 1 ln x plus the integral. This in here is going to become x to the minus 2 dx, and then evaluated from 3 to t. And then we get limit t goes to infinity, negative x to the minus 1 ln x, and then minus x to the minus 1 evaluated from 3 to t. Okay, let's go ahead and plug in these bounds and also rewrite these x's to the minus 1 in the denominator. So I now have the limit as t goes to infinity. Looks like I would have negative ln of t over t minus 1 over t. And then minus, when we plug in 3, looks like negative ln of 3 over 3 minus 1 over 3. Again, this over here is just a number, so we don't really need to worry about that. We just need to analyze this here. Well, now this term, certainly, we know that this is just going to approach 0. This one, though, unfortunately, is an indeterminate form. It's infinity over infinity. But we can probably anticipate what's going to happen. Again, we can use our little ordering of expressions. We sort of claimed that polynomial and power expressions are a whole level faster than logarithmic ones. So that means that in this situation, since the logarithm is in the numerator and the polynomial is in the denominator, the polynomial is going to outpace the logarithm in the long run. This denominator should win out in terms of growing more quickly. We anticipate that this is going to go to 0. Let's actually see that. It's in an infinity over infinity situation. So we can go ahead and apply L'Hopital. Notice there's no need to use like a replacement theorem because t is working with this x variable, which is assumed to be continuous. So if we L'Hopital this, we have the limit as t goes to infinity, minus 1 over t, and 1, and of course, as predicted, this is a constant, this goes to 0, this thing does equal 0. So this whole thing goes to 0. So we get that the improper integral converges. So by integral test, so does the sum ln of n over n squared. So this is sort of interesting. What the whole point of this was is that this is saying that while this ln is getting larger and larger, right, this numerator gets larger and larger, it's getting infinitely large, that n squared is still the dominant term. And we know that things with an n squared denominator end up going ahead and converging. So that ln of n doesn't have an impact there. Now, what if this thing had been the sum of n over n squared? Could we just say, oh, well, the n squared wins out? Well, not really, because this time they're both of the same type. They're both polynomial. So we would need to simplify it to be like 1 over n, and then it would actually diverge. So the whole key here is not only that the n squared is faster, but it's a different level faster, right? We're not just saying that it's faster because it's got a higher exponent. We're saying it's faster because it's fundamentally a different type of expression. It's polynomial, whereas the natural log of n is logarithmic. Okay, let's go ahead and try another one. So now what I'm going to do is I'm going to put my polynomial in the numerator, and I'm going to make it ridiculous, n to the 100, but I'm going to put an exponential term in the denominator. Now, if we go back and look here, exponentials are supposed to be a level faster than polynomials. So once again, what we anticipate is that even though the numerator is going to get massive quickly, in the long run, the exponential should be dominant. And the exponential, well, since it's in the denominator, is going to cause this to converge. So let's see how we'd analyze this. This will give us a chance to practice something like root test. So we're going to try root test on this. So for root test, also, I guess as a side note, I sort of was focusing a lot on the speeds here. All my examples so far, if we go back and we just take a quick look, this guy here, it would actually be absolutely convergent when we did this because everything has had always positive terms. So since it converges and has always positive terms, it would be absolutely convergent. Just realize that up top, the actual question specifically said absolutely convergent, conditionally convergent, or divergent. These conditionally convergent ones were never an option because, again, always positive terms. Okay, but back to this. Now we have this polynomial term getting really, really large, but we're saying that the exponential is a level faster, so we anticipate that this thing will still converge. And we're going to use root test to practice that. So to do a root test, we take the limit as n goes to infinity, absolute value a sub n to the 1 over n. So that's going to be the limit as n goes to infinity, n to the 100 over 2 to the n in absolute value, all to the 1 over n. Is the absolute value necessary? Well, again, always positive terms here, so not really. We can just go ahead and apply the 1 over n exponent to each thing. Power to a power you multiply, so it looks like we get n to the 100 over n, and down here, n times 1 over n, that's just going to be a 2. Now, this is a tricky limit because technically this is infinity to the 0, which is indeterminate form. But we sort of learned a trick. We know that the limit as n goes to infinity of n to the 1 over n is 1. That was an important limit we sort of mentioned about root test. So let's build that limit in here. We can see that this limit as n goes to infinity is really n to the 1 over n to the 100 over 2. And if we look at that, well, limit as n goes to infinity, we know that that goes to 1. So we get 1 to the 100 over 2. Now 100 is a finite power. It's a large power, but it's finite. And you can see that that comes out as 1 over 2. For root test, remember you compare it against 1. This is less than 1. So this implies we have an absolutely convergent series. So again, this sort of establishes what I was saying about the speeds of these expressions. That polynomial, it gets large really fast, but not at the same speed that the exponential does. So this one collapses to 0 very quickly, and that means that the series will converge. In this case, we have absolute convergence there. Okay, let's try another one. Same pattern. We're now going to put the exponential term in the numerator, but put something that's supposed to be even faster than it in the denominator. So again, sort of ridiculous just to really drive home the point, but I'll have my numerator now be 100 to the n, so an absolutely incredibly fast exponential. But I'm going to put a factorial in the denominator. And it'll turn out that once again, since the factorial is a level faster than the exponential, this thing will converge. Let's go ahead and see how we can do that. Because it's got a factorial in there, we should use ratio test. So we're going to try ratio test here. So we're going to do the limit as n goes to infinity, absolute value an plus 1 over an, which is the limit as n goes to infinity. An plus 1, that's this plugged in with n plus 1, so we would have 100 to the n plus 1 over n plus 1 factorial, divided by, and then an would be 100 to the n over n factorial. Then all of this is always positive, so we can drop the absolute value bars and also swing this up here and this down here. So we should get the limit as n goes to infinity. We have 100 to the n plus 1 times n factorial over 100 to the n times n plus 1 factorial. Okay, let's do the easy simplification first. 100 to the n plus 1 and 100n is just going to leave us with a single factor of 100. So limit n goes to infinity, 100 times n factorial over n plus 1 factorial. Now remember, n factorial, that's n times n minus 1 times n minus 2 times dot 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 times 2 times 1. And n plus 1 factorial is n plus 1 times n minus 1 times dot 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 times 2 times 1. So that means these will all cancel except for the very first thing in this one, n plus 1. So this should simplify as the limit as n goes to infinity, 100 over n plus 1. A fancy way of saying that is that n plus 1 factorial is really n plus 1 times n factorial, and then the n factorials cancel. Okay, what about this limit? Well, 100 is a big number, but it doesn't change. So as n goes to infinity, this is 100 over something that gets larger and larger. This goes to 0. That is less than 1. So once again, we have something that is absolutely convergent. So whole point here is that, yes, the exponential gets really large really fast, but the factorial is a whole level faster. The factorial is in the denominator, so it is going to win out and make this thing collapse to 0 very quickly. So again, we have an absolutely convergent series. Okay, now we said that we should have something even faster than the factorial, which should be that n to the n. So let's try another one. We'll put that n factorial in the numerator, so now the numerator is going to grow really, really fast. But let's put n to the n in the denominator, which is supposed to be a whole level faster. Once again, we would anticipate that this should converge. Let's see how to analyze it. Again, it has a factorial, so let's try ratio test. So we need to do the limit as n goes to infinity, an plus 1 over an. Limit n goes to infinity. Well, an plus 1 is just going to be n plus 1 plugged into that. So n plus 1 factorial over n plus 1 to the n plus 1. And then divided by, well, a sub n is just n factorial over n to the n. I think we may have even done this once in a previous video, but let's just go ahead and continue through. Absolute value bars, again, unnecessary, so we can just drop those. Limit n goes to infinity. We've got n plus 1 factorial, n to the n, and then we have n factorial and n plus 1 to the n plus 1. Okay, we just did an example of simplifying these, so let's go ahead and do that. And this is just going to give us an n plus 1 here. So we're going to end up with the limit as n goes to infinity. We've got n plus 1 up top, n to the n, and n plus 1 to the n plus 1. Okay, at this point, we can cancel a single factor of n plus 1 with this, and just have this be n plus 1 to the n. So, limit n goes to infinity, n to the n over n plus 1 to the n. Now, this is tricky because we actually have an infinity to the infinity over infinity to infinity. This is really indeterminate, but everything's to the nth power now. So we can rewrite this as the limit as n goes to infinity, n over n plus 1 to the n. And we talked about how 1 plus 1 over n to the n, that goes to e. That's the definition of e. This is the reciprocal of that, so this limit, which I believe we did do in a previous video, comes out as 1 over e, because it's the reciprocal of the definition of e there. So this is equal to 1 over e. You guys, if you want, you can check that by actually doing L equals that limit. And then since it is an indeterminate form, you have to use the trick of applying the natural log of both sides and working with that. We did that in a previous one, so we know that that is 1 over e here. 1 over e is less than 1, which implies that this is absolutely convergent. So again, this should reinforce that idea of these levels of speed. The factorial we saw is incredibly fast, and so having it in the numerator seems like that should make these things get really large really quickly. But by putting an n to the n in the denominator, not only does it mean that the things collapse to 0, but they collapse to 0 so quickly that the sum, the infinite sum of those infinitesimally small terms, still comes out as a finite value. Okay, now, in my list, I sort of put n to the n as the sort of end of it. Of course, in terms of basic expressions, that's probably the order we mostly encounter. But I'd like to do one last example to show you that, of course, mathematics can always be continued on. And there is, of course, something even faster than n to the n. Now, I'm not going to list that, but I would like to see one example of it. So what I'm going to do is I'm going to put n to the n in the numerator. And the way I'm going to build something that's even faster is I'm going to put 2n factorial. Now, 2n factorial, you have to make sure you see here that 2n factorial, as I've written it, is not 2 times n factorial. 2 times n factorial would just be doubling n factorial. It'd be fast, but not really especially faster. But 2n factorial is saying let's go twice as far in the factorial than normal. So if you have an n equals 2, you don't have 2 factorial, you have 4 factorial. If you have n equals 10, you don't have 10 factorial, you actually have 20 factorial. So 2n factorial is way, way faster. So let's see if it's fast enough to beat out this n to the n. So since we again have a factorial, we'll try ratio test. We'll get our limit as n goes to infinity, absolute value an plus 1 over an. Again, n plus 1 here is going to be n plus 1 to the n plus 1 over parentheses 2 times n plus 1 factorial. And then in the denominator, we have n to the n over parentheses 2n factorial. Okay, let's go ahead and simplify. We'll also drop the absolute value bars here. So we have limit as n goes to infinity, n plus 1 to the n plus 1, 2n factorial over, and in the denominator, it looks like we have n to the n. And if we simplify this, 2 times n plus 1 is going to be 2n plus 2. So we have the 2n plus 2 factorial. Okay, how are we going to simplify these? Well, let's just take a little moment to sort of think about this guy here. If we think about 2n plus 2 factorial, that's 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times dot 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 times 2 times 1. What do we notice about that? Well, all of this stuff is what makes up 2n factorial. So this is really 2n plus 2, 2n plus 1 times 2n factorial. So if I cancel that 2n factorial with that, I will be left with both 2n plus 2 and 2n plus 1. That should make sense because what does 2n factorial do? It goes through its factorials twice as fast. So when we cancel, we're not left over with just one term. We're left over with two terms. So now if we look at that, we have that this is the limit as n goes to infinity. Up top, we still have n plus 1 to the n plus 1 over n to the n. And now we have 2n plus 2 and 2n plus 1. Okay, let's do a little trick and factor a 2 out here. So we can think about this as the limit as n goes to infinity, n plus 1 to the n plus 1 over 2 n to the n plus 1, 2n plus 1. Now we can cancel the n plus 1 with one of the n plus 1s up top. And we can get this thing into limit as n goes to infinity, n plus 1 to the n over 2 times n to the n times 2n plus 1. I'm going to put these two terms together now. So just by rewriting, we should have the limit as n goes to infinity, n plus 1 over n to the n over 2 times 2n plus 1. Okay. Why is this important? Well, if you take the sort of negative view of this, it's not great, because up here we have a 1 to the infinity, which is an indeterminate form. But we actually know what happens up here. N plus 1 over n, that's 1 plus 1 over n to the n. That's the definition of E. So this piece here, this is headed towards E. But what about down here? This is 2 times something that goes to infinity. So this is approaching E, which is a number, over infinity. So this is going to equal 0. Let's not use the colors for that part. Infinity, which is going to approach 0. So what do we know about that? That is less than 1. So we have absolute convergence again. So even though we put the fastest thing that we've discussed so far, that n to the n in the numerator, by putting a 2n factorial there, the 2n factorial not only gets the terms to go to 0, but they go to 0 so quickly that the series still sums up to a finite value. So as you can imagine, you could then try to think of something that's even faster than 2n factorial. And you could continue on and on, going back and forth and always finding level faster of expressions. But for us, I really want you guys to think about that logarithmic, then those powers, then those exponentials, then those factorials, then at the very end, that n to an n, because that really puts together the polynomial and the exponential expressions. The last thing that I'd like to say here is that I had all of these turn out as absolute convergence. You should keep in mind that if you had the reciprocal of these, you could use the same arguments to see that all of them are divergent then, right? If we go back to where we really started analyzing this here, if we had n squared over ln of n, well, the n squared would win out over ln of n, and it would diverge. You could do that through tests for divergence if you wanted to. If you had 2n over n to the 100, well, the 2n would be faster than the n to the 100, so it would diverge. You could again use tests for divergence, but it would require like 100 applications of L'Hopital's rule, or you could just use root test and you'd get a limit that's greater than 1, so it would diverge. If you had this one where the n factorial was up top, so you had n factorial over 100 to the n, then it would diverge because the n factorial would be a level faster than 100 to the n. You could still use ratio test. And same thing with these. If I had switched the locations, they would diverge because we're really just trying to get you guys to understand the speeds of growth of these different expressions. Okay, so that was a lot of examples. We still have one last part of our summary. If you put together what we've done so far, in the first part of 11.7, we sort of recapped what it really means to converge as a sequence and converge as a series, and really making sure that we understand absolute conditional convergence and divergence. Now we've talked about this sort of thing that we've hinted at many times, which is the speed at which these things grow, which determines whether or not they converge. The last thing we'd like to do in our summary is to sort of go back and sort of discuss how do you choose an appropriate test to actually look at sort of a given series. Obviously, in this video, there were several that had factorials, which we knew were just a given ratio test, but there were some, like this one here, where it's saying, so how do you know to pick out the root test as a good choice? Or this one here, how do we know to pick out the integral test as a good choice? So in our next video, we'll talk about strategizing the choice of test based on the series that you're given.